This video will be a detailed tutorial on how to check the high voltage system. By detailed, I mean we'll cover all three types of high voltage shorts. The first type is the 49 short. The second type is the MOSFET highlight short, which is also part of the high voltage short system. The third type is also a highlight short, but it occurs within a group of coils that are connected in parallel. This means that if one of the highlight modules is shorted and the coils are connected together, it can cause multiple shorts, making it harder to identify the problem. So there are three types in total. The 49 short, the MOSFET highlight short, and the highlight short within the group that shares the same coil as the mod highlight short in the group where the coils are connected together, meaning the coils are linked and the mod highlight short occurs right there. So there are three types. Let's start with the 49 short first. Don't forget, when troubleshooting the high voltage system, you really need to start from the high voltage circuit assembly. Let me show you the groupings of the high voltage system first. Actually, in the step-down circuit, there are two MOSFETs, right? And one PWM controller, just like I explained in the previous video. Now, in the case where the MOSFET high drive is shorted, if it's a highlight short, the 19-volt current will be forced into the coil because it's shorted between the drain and source pins. Once it enters the coil, where does the current go? It will flow to the load, whether that's the CPU, RAM, graphics card, or whatever else. This can cause significant damage to the motherboard if the MOSFET high side is shorted. So, how do we measure or check if the MOSFET high side is shorted or if the capacitor is shorted like this? Because the components related to the high voltage system include the MOSFET high side and the 49, but the current must pass through the high voltage circuit assembly first. When the 49 is shorted or the FET high side is shorted, it will draw current through the component through this power delivery circuit, causing a short. When it shorts, nothing actually happens. The device still works. That's because it's a positive to positive short. If you think about it, this side is positive and so is this side. The power delivery circuit is just passing positive voltage. So a positive to positive short doesn't cause any issues. However, it won't charge the battery because the charging circuit controls this power delivery section as I've explained before. Therefore, after we finish repairing the high voltage section, we need to check and repair the power delivery circuit, or what I call the high voltage soft start section. We have to check first that it's not shorted by measuring across it between ground and the source pin. Measure between drain and source, ground and source pins. You can also measure from this side to the middle pin on the other side. Just make sure not to touch the gate pin. The gate pin is at the edge or pin 4. So after we've finished repairing the high voltage section, we need to measure the high voltage power delivery circuit. It must not be shorted, otherwise if you send the device back to the customer, it won't charge the battery. Alright, let's have a quick briefing before we start checking. Okay, let's begin the repair inspection. I'll start by using a digital multimeter, which will be displayed on this screen. I've set it to the diode mode, which looks like a diode symbol, an arrow like this. Set your meter to diode mode and use the black probe to touch. Just like I taught before, you can use the black probe from the previous method, which is easier, or you can use the red probe from the previous method as well. The original value should read 0.5, but if you use the black probe from the previous method, the value will quickly show OL. That way it's easier and simpler to remember. Okay, now we're measuring at point 49. How do we know where 49 is? We only select one 49 on the board. Find the coil first because 49 starts from the coil. Find the coil on the board. The coil is separated by two resistors and then 49. Sometimes the coil is separated by just one resistor if it's a UOB, or the coil can be separated by a PDM as well. Or it could just be a PDM because the MOSFET is integrated into the PDM. So we have the hard coil, the PDM, and then the large 49C component. We can choose that option too. In the case where it's a FET, it's simple. Just look at the coil, then the two FETs and the 49. You can pick any one corner, just choose one corner. Because with the 49, you don't need to select the whole board. Just pick one component. Don't forget that. Pick the wrong one. It could change your life. You'll end up connecting power to the low voltage system. Because, for example, a capacitor like this looks just like a 49, but it's actually a low voltage capacitor because it's not attached to the motor. It has to be the core, Aminfid, and then 49. Remember that. You have to trace it that way, with a coin in the middle, then MOSFET, and then 49 like this. Now let's measure it. The side with the round dot is the standard. For those who pay close attention, it should be the round dot, the mass source. If it matches with 49, that spot will be ground. That's an easy way to identify it. This is the pole. But if you don't want to check it this way, you can just measure it. This side is ground. This side should show OL if it's normal, if it's a regular board. But this set here, it's not normal, you see? It's reading 0.000 volts, which means it's shorted on both sides. I'm keeping an eye on this. Let me show you by touching the meter leads together. See? It's showing 0, which means this point and this point are touching, just like when I touch the meter leads together. You get the principle, right? So this is ground, and you can't have ground twice. What kind of component has ground on both sides? None. That means it's definitely shorted. This is a high voltage short. We don't need to measure the other 49 points because the whole board will be shorted the same way. The entire board, all 49 points will be shorted. When you check at 14 and 19, they're all shorted. We can immediately tell that this is a capacitor short. If it were a MOSFET short, it would be different. For a MOSFET highlight short, the diode reading would show a value, but not zero. Let me explain this first. The diode value would show up, but it wouldn't be zero. But if the diode reading is zero like this is the negative side, the circle is the negative, and this is the positive side. If it's zero like this, it's considered a freeze. But if you encounter this in a gaming notebook, if you measure here and it reads 0.000, that means it's a 49 short, right? Not yet. That's right, if it's a gaming notebook, let me warn you in advance. If it's a gaming notebook, we need to switch our meter to measure ohms instead. So try measuring it. At the ground position, the ohm value will be low, around 0.13 ohms. But on the positive side, it won't be exactly the same. Notice that. It won't be exactly 0.13 ohms. The ohm value will be a bit higher, which lets us immediately know that this is really the positive side. You can also use a digital meter to find the positive and negative sides. But if you want to use a power supply to find the circuit information, that's possible too. For beginners, I'll teach you how to use a power supply to find the circuit information in this case. We'll immediately know it's a capacitor because it starts with 0 as well. 0.16, 0.10, like this. They're close in value, so this is a free tip. Of course, if it's a shorted capacitor, you'll see 0.10, 0.16, but you'll know that this side is the positive side, and this is the negative side, because the side with the lower ohm value is the negative side. This is how you can tell the negative side. The positive side. Now, if we want to supply power to find the positive or negative side, that's possible too. But in the case of a gaming notebook, if this side reads 1 ohm, right here, 1 ohm, about 1 ohm, or 0.7 ohms, 0.6 ohms, that means it's a MOSFET high side short. If it's a capacitor short, the ohm values will be very close to each other. But if the ohm value on this side is much higher than the other side, even twice as high, you can compare it like this. For example, the ohm value is 0.140, 0.15, and if it's double, that's 0.300. Year 29 or something like that, this is still considered a capacitor short. But if it goes much higher, like around 0.4 or 0.5, we'll immediately know, okay, that's a high side short for gaming laptops. And the short usually happens around the graphics card and CPU area because the resistance or ohm value will be very low for gaming laptops. I'm explaining this in advance because I'll be demonstrating both regular notebooks and gaming ones. Let's start with the standard type first. In this case, it's definitely a short, because it shows 0.2 on both sides and the readings are close to each other. This is measured in ohms, but you can also measure it in diode mode. For regular notebooks, the kind used for typing or general tasks, not gaming laptops, you can troubleshoot them like this. If it shows 0.2 on both sides, it's definitely a short at the capacitor, a 4-shot short. In that case, you can inject power right away. If it's a 4-shot short, you can inject power immediately. This is because if it reads 0 ohms on both sides, it means that when the capacitor is shorted, these two sides are directly connected, so it reads 0. If you supply 19 volts of power here, it will go straight through this spot. That's why it will show a 0 reading. But if it's a fake mod highlight short, when you check it with the probe, it's shorted together, but we still measure 49. So the reason it doesn't drop to 0 at all is because there's another FEDLO mod acting as a barrier. So it doesn't flow down to this point here. This one isn't shorted, this one is okay. That's why the measured value isn't 0, you get what I mean? So if the fit mod or something is shorted, the measured value won't be 0. But if it's a C short, the measured value will be 0. But if it's a gaming, let me repeat that one more time so it's not confusing. Now, let's get back to the point where we're going to do the repair. The way to check and repair is that we need to inject power right here. Don't supply power to the Raptor because currently the power control unit here is a tunnel which has a protection circuit or a power cutoff. So if there's a short in the high voltage section here, it will immediately cut the power. If we supply power here to find the short or the hot component, it can cause problems because the power will pass through the mod and this power control unit and then go to the series short, which can cause the MOSFET here to short as well. As I mentioned earlier, the device works normally but doesn't charge the battery. Remember, it doesn't charge the battery. Now, what we need to do is inject power at pin 49 instead, which is the safest method. It's simple. We need to use this and then use alligator clips like these, connected from the power supply. The red and black clips are connected directly from the power supply. Then inject power at pin 49 on both sides to determine which side is positive and which is negative. Use the black clip it onto the ground right into the slot, okay? We don't need to use the meter. Just use the tip of the needle to insert and inject the power. Here, we can't inject 19 volts because the voltage is too high. When we're supplying power, we can set our meter to the voltage range first, then adjust the voltage on the power supply. If your power supply has a voltage adjustment knob, turn it down. If it's digital, just press the button to lower the voltage until it's only about 1 volt or 1.2 volts. Either is fine. About 1 volt is enough, or even less than 1 volt, like 0.8 or 0.9, that's fine too. It can be less than 1 volt, or you can set it exactly at 1 volt, something like that. Just don't go over that, then connect it. Use alligator clips to clip onto the tip of the meter's needle. The meter won't get damaged. You can keep it set to the voltage range, then inject power into both sides. Don't forget, if positive touches negative, let me show you by connecting the supply to this. See, when positive touches positive, the current spikes. The current is about 4.4 amps, 4.5 amps. When positive touches positive, the current will be high. It's the opposite of measuring ohms. Earlier, when we measured ohms, it showed which one was. It's more expensive to be negative, but in this case, whichever point has more current is the negative side. It's the opposite because, see, I'm confused. When positive touches negative, the current is high. The side with the higher current is the negative side. Let me try injecting power into these 2 points. Watch closely. I mentioned from the start that the side facing the round mark will go to the side I mentioned first. Now let me inject power here. This one draws 4.6 amps. See? 4.6, which is pretty close to when we injected power over here as well. It's similar, right? 4.6, 4.7, isn't it? So it's negative. You can tell it's negative. That's the ground, the chassis of the device. But on the other side, and the current is 3.6 amps. See, it's less. This side is less, so it's positive. We'll immediately know where the positive side is, which just now when I measured with the meter, it showed that the positive side is on this side. For this, I can probe any of the 49 points, because when it shorts, this one shorts, all the others short as well. When the others short, the meter doesn't tell you which component is faulty. It only tells you the faulty group, so we still have to find the faulty component ourselves because of the supply. First, use the meter to check in a cold state, meaning without plugging it in. Use the diode mode to check. If it's shorted, then we inject power. To inject power, we need to find the positive side. Where is the positive side? We have to use the power supply to find it, just like earlier. We know the positive side is on the left, so we inject power there. Now we should be able to find the shorted component. The one that is shorted will heat up. A current of about 3.9 amps is enough to detect the hot part, but you might not feel it by hand because it is too little. You might need to use an infrared camera or something similar to help, but you can also try feeling it by hand. There should be some heat. Try tapping around like this. If you want it to get hotter, increase the current by raising the voltage. Right now, I'm using a voltage of 1.05. Now I will increase the voltage to 1.2 and see if the heat increases. See, as I increase it, the current goes up to 4.5 amps and it will keep rising like this. Try adjusting it a bit, 0.35, but it should not go over that. At around this level, the current will be about 5 amps or so, and a lot of heat will be generated. Now you can use an infrared camera to check. I recommend using an infrared camera. Just keep supplying power and use the infrared camera to see where the heat is coming from. It's about 45 degrees. The infrared camera will clearly show it. If we point our hand, you'll definitely see our finger on the screen. You can observe where the precise position is, but it's not exceptionally clear. The infrared data isn't sufficiently clear enough to accurately tell exactly which specific part it is, but you can certainly see the general area right around here. So it's in this particular area, this exact position. Here, I'm supplying electrical power right here, but the heat is actually generated over here. Do you see? I'm connecting the power over there, but here, this is high voltage system troubleshooting. There's still no progress because the current is still low. Let's try increasing the voltage. The fuse is starting to melt. See? Heat is being generated and the fuse is melting. This is just an approximation. If you want to see the heat, then increase the voltage, but I don't recommend it because right now you can just touch it lightly and you'll know. If you want to see it with smoke coming out, you can do that too. See? It's boiling now. This is over 6 amps. Right here, the fuse is bubbling. Let me show you a clearer picture. I'll increase the voltage to about 3 amps. Now there's smoke. This is 10 amps. This isn't good because it could damage the board's layers. Actually, with real heat, just 3 amps is enough for the infrared camera to detect it. It can already find the problem, but this is way too high. Normally, you should use about 1 volt to about 1.2 volts is enough for the infrared camera to detect it. That allows us to eventually find the faulty component. Now, once we found the faulty part, what do we do next? We use a hot air blower to remove it, setting the temperature to around 400 to 430 degrees. The airflow depends on what you're comfortable with. Then put on the air nozzle and you can blow a little bit onto the component. Just now, I already put the nozzle on. After putting it on, then if your hands aren't steady when using the hot air blower, Just use tweezers to hold it in place, use longer tweezers, and blow the hard air around. Blow while holding it with the tweezers like that, so it will not jump off and stick to the tweezers again. As for the solder we removed, we do not need to add more, because there are several 49-volt or high-voltage printer components. There are many of them, so we do not have to add more solder. Now, let us recheck or double-check here. The short circuit here should be gone now, right? Let me check with the meter first. Now, place the red probe on the ground. Double-check at the 49. See? The diode value has increased. Now it shows OL. See that? Normally this one is ground, which is 0. Now we've finished the repair. At this point, if you want to measure voltage, you can go ahead and supply power. You can try powering it up, but most importantly, don't forget to check the power rail thoroughly first to make sure it's not shorted. Try measuring the middle pin on that side and the middle pin on this side. Always measure in diode mode every time after you recheck. Then check the power rail set that's close to the adapter. In this area, there will be a diode. Just measure across it. This one shows OL, which is the diode value on this side. The diode value on this side is okay. Normally, for this power rail point, you measure between the side with the round marking and the opposite side like this. See? It reads 0.00 on the display. As you can see here, this MOSFET is shorted, which means our power rail is shorted. But this device can still be used. It works normally and supplies power as usual. However, it will not charge the battery easily, because when this part is shorted, it will not charge the battery. So, after we have finished repairing the high voltage section, we need to check here and replace the component properly. Only then will it charge the battery. Okay, so now I will supply 19 or 20 volts to measure the voltage. Set the meter mode to the voltage range. Set the meter to DC, use the black probe on ground, and measure the voltage. Plug in the adapter to supply power to the system, and then read the voltage at 0.49. Measure the voltage at 0.49 like this. You'll get 19.9 or about 20 volts coming in. This means it has passed for the high voltage system check. If there are two faulty points, you can repair them. Even if there are more, you can still fix them. Just troubleshoot step by step. If you find another shorted component, just fix it. So that's it for repairing the high voltage section in the case of a 4-point short. Next, we'll check and repair the case of a MOSFET trick short. Alright, this is the same main board, but in this case, it's also a high voltage short. However, this time the short is caused by the MOSFET, not by 0.49. What's the difference? If the short is in the MOSFET section, it's different in that. If it's a high side MOSFET, this is a high side MOSFET. If it's shorted between the drain and the source pins, when you measure the diode mode, the value will show up, not 0.0000. If you see a value, it means the high side MOSFET is definitely shorted. For 0.49, when we measure it, it just shows OL. Remember, if we inject power, all the current we supply will flow directly to the load. That's dangerous. When something is shorted, the current will go into the load. So, the voltage we should supply should be no more than 1.2 volts, because that voltage level won't harm anything. It won't damage the CPU or the shorted IC. We can supply 1.2 volts and use an infrared camera to see which MOSFET is heating up. But I've tried it and it's difficult because it doesn't really get that hot. If you want it to get hotter, you have to increase the voltage, but if you do that, the current will go into the load. The higher the voltage you supply, the hotter the CPU will get. If it gets really hot like that, you should stop immediately. That means the low voltage system is about to fail because you're supplying too much voltage, in the case where the MOSFET high drive is shorted. So the correct method is that we don't usually inject power. Instead, we prefer to use a meter to measure. You can measure across the drain and source pins of the MOSFET, but if the MOSFET is embedded or integrated into the PD, it will make it difficult for us to measure. Or if two MOSFETs are combined into a single unit like a UFET, it will also be hard to measure. The easiest way is to measure across their own connection points. For the high side MOSFET, its connection point is the drain pin, which connects to the 49. Which we regularly measure anyway. As for its source pin, it connects to the coil. So we should measure across the 49 and the coil. This is how you measure the high side MOSFET output without having to power it up. Just use a multimeter to measure it. I'll try both methods. First, I'll supply just about 1.2 volts to see if it detects a fake short. Don't supply more voltage than that. If it doesn't detect anything, then just use the multimeter method. I'll use the measurement method first before powering it up to see what the result is. So the method is to set the meter to diode mode. We measure at pin 49 using this side as ground. The 0.000 side here should not be chassis ground. It should show OL, over limit, but if it shows a diode value of about 0.4 volts, then we immediately know this is a high side MOSFET short. Because if the high voltage side shows OL or above 2 volts, that's fine. 2 or OL is okay. But if it shows a value starting with 0 point something, that's not right. If the high voltage side is shorted, it's 100% short. But in this case, it means it's a high side short. Now here's a simple and quick way to measure. We measure between pin 49 and each coil. This pin 49 is already the positive side. Our meter is already set with the red lead on the positive side. Move the black lead away from ground and instead touch it to each coil one by one like this. If it shows 0.2, it passes. If you see a reading of 3000 or so, just ignore it. If the value is higher, that's fine too, just as long as it is not 0. If it is 0, that means that point is where the high drive is shorted. This one isn't it. This one isn't it either. This one isn't it, see? We're only moving the black probe, we're not moving the red one. Pin 49 is already connected to everything, so we just keep moving and probing along. See, this one reads 0.000. This shows that this point on the positive side of pin 49 is connected here, like there's continuity between them. That means the drain and the source of the MOSFET high side here are shorted. It's shorted right here. Now we know that the MOSFET high side is shorted at this spot, and we didn't even have to power it on. But the thing is, the meter doesn't tell us exactly which one is faulty. It only tells us the group that's faulty, which is this group. How many MOSFETs are there? 2. So we need to screen them to find out which one is the high side MOSFET that's faulty correctly. But according to the rule, we know the high side MOSFET is the one that doesn't have any pin connected to ground at all. The drain is connected to pin 49, the source is connected to the coil, but none of its pins go to ground. So even if it's shorted between the drain and the source, it still doesn't go to ground. But the characteristic of the low side MOSFET, this one, is that it does go to ground. That means the low side MOSFET is grounded. The high side MOSFET, even if it's shorted, doesn't go to ground. So we just measure and compare to ground. We measure to see which one is grounded, and that's the low side MOSFET. It's simple. The principle isn't complicated at all. Let's try measuring here to see which one is grounded. Put the black probe on ground as mentioned, and then just randomly probe these two components. Randomly touch each pin. See if any of them read 0.00. There should be one that's connected to ground. This one reads 0.3. This one is connected to ground, so we immediately know that this is the low side MOSFET. Therefore, the one we want is this one. We can immediately identify the shorted component, remove it, and that's it. Now, I'll switch to supplying power. First, set the meter to volts, then supply about 1.2 volts, as mentioned earlier. When supplying power to the positive side, how do we know which side is positive? In the case of the MOSFET we like, we can tell which side is positive because the positive side is the one where the diode reading is not 0. See, this one on the left is the source, which is ground. So we'll inject power here. No need to worry about positive or negative because the value. The rule is, if it's not 0, that's already the positive side. Right here, this one is the positive side where the red probe is touching. This is the positive side, meaning we supply power right here. Okay, let's supply power. 1.2 volts. Is there any current draw? Very little, see? Very, very little. Just about 0.02 amps. There needs to be a load for it, which means the power must go into a load as well. The current draw from the load I'm talking about is the RAM at this point. This is the point where power is supplied close to the RAM, so we need to install the RAM as well. See, there's a risk, because if you put a load in, there's a chance that all the power will flow into the load. But this RAM is DDR3 RAM, it uses 1.5 volts. So if we set it to just about 1.2 volts, it won't break. Supplying power to the load like this won't damage it. So when we supply power, the current will increase a little bit, like here, it's 0.022 amps because there's a load and the power is going into the load. The load completes the circuit. The circuit I mentioned, you need to have a load connected to it. Only then will you find the part that gets hot. For example, if there's a short at the CPU and we remove the CPU, like this, for the machine, you can remove the CPU. If you take the CPU out, the short circuit disappears. There just needs to be a load, that's all, for it to work. The heat only increases a little, but not much. 25 degrees, we probably won't see that. Let's increase the voltage to about 1.35 volts. The current will go up a bit, see, just a little, 1.5. So at 1.5 volts, the current is 0.03 amps, which causes new heat, but it doesn't really happen. Notice that this method doesn't work very well if you increase the voltage more than this, the heat will occur at the RAM instead, because all the power is running into the load at the RAM. Therefore, supplying power or using a power stick is not suitable for finding the shorted component or highlighting the short. Using a power stick is not as effective. Measuring with a multimeter is much easier. Right now, the meter already tells us that this is the faulty component. I will remove it now, and this time I won't supply power. You see, when I supplied power, I couldn't find the hot component. It didn't work. So I recommend that using a multimeter to measure is better. Just measure when it's cold. Use the diode mode. All right, now I'll remove the faulty MOSFET. Okay, I've removed the MOSFET. Now I'll retest it using the diode mode as before. Let me check the mid pin in diode mode at 0.49 to see if the short is gone, especially at the middle pin. When the MOSFET was in, it was 49, right? Now the diode reading has increased. Now it's showing OL. We've successfully repaired it. When the reading goes high, it means we've fixed it. We found that the MOSFET was faulty, so now we'll replace it with a new one. If we don't replace this part, the power supply won't work. You can't just refresh or reset it. You have to replace it. In newer models, the casing is designed so you can't put the part back in the wrong way. See? There's a casing. The casing has a full leaded PCB pattern like this. When you turn it this way, you can't insert it backwards. To install it, you can use a hot air gun to heat the main board first, or you can add a little bit of flux, which is also good. Apply some flux first, and then gently bring it in and align it. Slowly push it in, making sure this corner is aligned first, then push it in here and let go. Make sure it sits flush first. You can adjust it again later. Some people like to make it look perfect right away, but if you use the hot air for too long, it gets really hot. Once it gets really hot, the board can potentially swell. Try to stop and then carefully adjust it again if absolutely needed. Squeeze the tweezers firmly together and meticulously adjust left and right until it's perfectly straight. Try heating it in several gentle rounds. It's much better than attempting to do it all at once. After it's securely in place, now we will carefully reflow it again. Okay, that's completely done. Since version 2, it has consistently been OLED, so that's perfectly fine. Now let's look at another interesting case, which is a mod trade short, but in that particular case, there are indeed coils connected together. It's hard to find the exact shorted IC because there's only one group, but when you measure, several ICs show as shorted since they're connected together. So we need to know how to troubleshoot in cases where there are many coils linked together, like in the graphics card area or in newer CPU models where multiple coils are connected at several points. This makes it difficult to pinpoint the internal short. Next, we'll talk about checking for a high-side MOSFET short. In cases where the short is at a shared coil position, this clip will teach you how to measure the high drive FET when there's a short involving multiple connected coils. For example, in CPU or graphics card positions, there are often several coils linked together. Especially in gaming laptops, there can be even more. So how do we know if it's a high-side MOSFET short and how do we measure it? Let's continue in this section. On Thursday, measure at position 49. This point is the ground. At this point, the diode reading is 0.0024, which clearly indicates a high side short. But if you should happen to encounter a specific case where the reading is exactly 0, then if it's 0 on both sides, don't be too sure that it's a C short. Measure it in ohms once more. If the ohm value rises to about 1 ohm, 3 ohms, like in the previous example, that's considered a clear buffer highlight as well. In this case, it's showing over 2 ohms, which also indicates a FET highlight short. For the repair inspection method, you can measure in ohms. I recommend measuring in ohms, or you can measure in diode mode. In cases where it reads exactly 0.0000 volts, I suggest measuring in ohms as it's easier. After touching the probes, move the probe to another point and see if here, it's absolutely 0 in front, precisely 0 ohms in front. The actual ohm value here is approximately 0.4 kilo ohms, which specifically refers to this particular point. Other points are definitely not 0 ohms. They're about 10 ohms, something like that. Now, if we carefully probe here, it's approximately 3 ohms, which is quite close, but not exactly 0. Here, it clearly reads 0.7 ohms right here. This is the spot. It's not exactly 0 in front like this, 0.6 ohms like this. That means the FET high is shorted right here, but it's shorted at these 2 points. See, here it reads 0.5 and this one also reads 0.5 ohms. Why do both of these groups, these 2 points, show a reading? Because these 2 coils are connected together. If I use the meter to probe at the end of So this set here, see, it reads 0.15 ohms. That means these 2 coil sets are connected in parallel again. Therefore, right now, it has to be in this group, these 4 components, but I don't know which one it is yet, which This is still a small case, there are only 2 coils, but let's say there are more than this. If there are more, then there will be more points where the highlighted MOSFETs are shorted, several of them. We could try removing them one by one, but using a meter to measure won't work because they're connected in parallel at many points. However, if we remove the CPU, the short will disappear because it's located near the CPU area. That's why you need to put a load on it, just like I mentioned. Now, I've removed the CPU and I'm going to measure the value. The value is better than the previous value.